Okay, so hi everybody, I am Claudia Toci. I am currently an ESO fellow in Gashing, and I'm very happy. I want to thank the organizers because I can present some of the results I had in the last years using the phantom codes. And I'm also happy that before my presentation, we discussed about vorticity, because it's something that I also found in some other works before using phantom. So I'm very interested if you try to do something regarding vorticity in gas clouds. So, but anyway, I'm not talking about vorticity, I'm talking about protoplanetary disks. I don't have to convince you that it's a great time for studying protoplanetary disks. We have many informations because we have a lot of observations, and those observations are made with different tracers. And I'm using this very beautiful image from Protostars and Planets 7, the paper of Anna, to show that basically, according to the trace we use, we may have information regarding how the mid-plane, the dust in the mid-plane is distributed. If we use the gas lines, we can say something on what's going on different scale height according to the tracer we are using. And if we use tracers like scattered light and direct imaging, we are basically probing the upper layers of the disks. And if we observe protoplanetary disks, or at least the bright ones, with those different tracers, we actually find that substructures, so gas and dust gaps, asymmetries, cavities, shadows, spirals are commonly revealed. And we see them using all those different tracers in more or less all the large sources. But I want also to make a point that actually, if we observe the same source, this is, for example, TW Hydra, with different tracers, actually what we see is kind of different, because if we look at dust emission, we are also sensitive to the dust drift inward, so disks are usually smaller, while scattered light and CO emission, for example, are tracing larger structures in the disk. So we have these substructures. We want to understand why we have these substructures in protoplanetary disks. And there are a lot of processes that can form substructures. Basically, we can divide them into categories: mechanisms that physically stop this radial drift, so the drifting of large dust grains towards the star, and mechanisms that form substructures. So you may actually see this kind of asymmetries or rings or gaps in the disk without actually physically stopping the dust that is still drifting inward. But we are very interested in the mechanisms that can form substructures trapping dust, because we hope that at least a few of them are created by young protoplanets embedded in the disk, interacting with the dust and gas itself. So what I do during my work, well, I do a lot of things, but I'm also very interested in connecting the physics, so the physical mechanisms that are at play in protoplanetary disks with the observations. And one of the ways I do this connection is using some numerical code, and specifically phantom, coupled with MC-FOST, because once you want to connect the physics to the observations, you also have to take care of the relative transfer of your simulation. And this is a very crucial point, because it's the way in which we as theoreticians connect with the observations. So specifically in the last years, among all the sources that are observed, I focused on sources that may host giant planets. So first of all, because I'm a bit, there are a lot of mechanisms to form substructures, so it's very difficult to understand which one may be formed because a planet is embedded. But we know that giant planets usually can make wide and deep gaps. So actually probably are the easier to see embedded inside the disk. And this is a unique signature of the presence of giant planets. And if there is a very wide and open gap, we can also try to see directly the presence of the giant planets embedded in the disk. And yesterday, Ian showed one example of a source in which we are actually doing our best, and maybe we did. We tried to identify a protoplanet embedded in the disk, still accreting. And also because, it's relevant for the formation of our own solar system, because our own solar system has 2 giant planets that, well, they're not as giant as the one we are revealing, but, they are Jupiter and Saturn, and they are very important for the evolution of the solar system itself. And also, we are now directly detecting exoplanets around other stars, but we are still biased towards the giant planets because they are the easier one to observe. And even if the planets we are revealing with ALMA are not the ones that we are revealing with the current missions for revealing exoplanets, it's very relevant to understand if due to the migration, those are the great-grandparents, let me say, of the planets that we are observing, or if they are a different categories of exoplanets that we still have to reveal. So I focus mainly on 3 sources, and I chose them because they may have the presence of double giants. Specifically, here I did a sketch to show what were the situation of the 3 sources. So the 2 giant planets may preserve a ring in between them, like in the case of HD 169142 and HD 10546, while in the case of PDS 70, there's a very wide and open cavity. And actually, those 2 planets are the ones that we directly revealed, probably because the cavity is so wide and depleted. So I want to briefly tell you what can we learn when we have a simulation and we compare our simulation with the observations. So first of all, here I'm showing the surface density of an output of my simulation of the case HD 169142 as a function of the distance from the star. So the dark blue is the gas surface density. The light blue is the dust surface density. Clearly, we form those dust rings. Dust is trapped in the pressure maximum of the gas. Then you select your best snapshot. So 1 planet is here, 1 planet is here. And this is actually the snapshot that Ian showed post-processed yesterday. To have this post-process, so to have the synthetic flux, you have to use some radiative transfer code, and specifically Phantom and MC-FOSS are very well coupled, so it's very nice to use them. You have to know your thermal structure, you have to fix some kind of dust properties, and this is very, very relevant because basically we are fixing the opacities of the dust. So it's a crucial point. And then if you want to properly compare your observations with your simulations, you actually have to take care of the noises that the several instruments may add to the observations. So this beautiful dust and gas dump becomes, after the radiative transfer, those 2 synthetic fluxes that you can compare with the observations of Fedele et al., for example, and Macias et al., and try to see if your model is relevant enough, so it's good enough, and if so, you can try to infer the planet masses and the position of those planets, and then devise new observations to try to directly detect the planets. But I mean, when I was in Australia and we were doing the Great Barriers conference, I was visiting Melbourne, then we went to the beach, but I also tried to model this very beautiful source, PDS 70, the one that has this wide open cavity. So again, the same game, you evolve your simulation, you suppose the presence of the 2 planets, and it's true. You obtain your wide open cavity and you preserve an outer dust ring. Then you select your best snapshot and you do the same play as before. You evaluate using MC-FOSS the synthetic flux, and you compare your predictions. For example, this is dust emission and this is gas moment 0 emission with the observations. This is Kepler et al. And also this one is from Kepler et al. And actually, for example, in this simulation, we also reproduce the presence of some material around one of the planets. And also the moment 0 is quite similar to the one observed. But then, as I told you, before, we want to do something more. So we wanted to use all the tracers that were available. And so we also tried to have prediction for the scattered light emission. But this is a bit more tricky because according to the different techniques that observers use for evaluating the images, you actually have to post-process also your synthetic flux, and this is what we did. So you treat your synthetic flux as a real image. You use the same pipeline, and those are our synthetic observations. And here, as a comparison, the observation of Müller et al. And also, I want to underline that we reproduce some features, we miss some other, but we learn something also not reproducing all the observations, because, for example, the fact that we miss some part of the flux here and here may be due to the fact that we don't reproduce the inner disk that we know is present in PDS 70. Then, you can also be contacted by people that are observing because they have a very intriguing source and they ask you if you can do a model to understand a bit more. So, for example, in the case of HD 10546, so it was known that there is a very, very faint outer ring, and please look at the sizes. So the inner part is, the inner ring is smaller than 50 AU in radius, while the outer one is basically almost 200 AU. So it's very, very far away. It's very, very faint. So how can we have such a faint ring in the outer part of the disk? So we propose that there is one planet inside here in the inner cavity to stop the radial drift and form this ring. And then we have one or maybe multiple giant planets in the outer part of the disk that is basically preserving this faint outer dust ring. And again, you can infer the mass and position of the planets by comparing your observations, your simulations with the observations, but also you may try to test your models devising new observations. For example, if you have one single planet, it has to be kind of massive, so it may open also a gap in the dust and in the gas, and so you may observe it. While if you have a system of lower mass giant planets, maybe they are not massive enough to open a gas cavity, and so maybe these two different scenarios may be distinguished by gas observations. Then I want to show you some other works. So this is not a work I did, it's a work that Pietro Curone, a student in Milano, did, but because he's not in Australia, and also he didn't join this conference, he's not showing this work. So I thought that could be nice also to show that if you have multi-wavelength observation of the dust, for example, so only dust without considering gas, you also can try to say something on the dust properties and also on the kinematics. So predict the kinematics of the sources with your model. Of course, the first benchmark is to compare your simulation with the observations. And for example, also in this case, the case of the low mass star Sida 1, we can actually say something on the mass and position of the possible planet that can be responsible for this inner cavity. And again, then trust dust properties and kinematics of your source. And this source is particularly relevant because it's a low mass star. And if a low mass star hosts a giant planet, it's a very nice scientific case to test. But then you can also try to study multiple stellar systems. This is my last work. We are finishing it, so stay tuned. So you may try also to use your model to try to understand which is the configuration of a specific system that is not well constrained. And this is the case of the Gigi Tau system. We have plenty of observations, but still it's not understood if this source, the binary, is it actually is a multiple stellar system, if the multiple star is coplanar with the disk or misaligned. And several works already explored these the two different possibilities, but we tested the two different configurations, and we showed that basically the different parameters for the orbits are actually impacting a lot the morphology, and we can try to use morphology of the disk to say something more on which is the most probable configuration, but also to test if our model, so what we know on the theoretical point of view, is consistent with what we observe. So I hope I didn't go long, but in summary, I'm very happy that I am comparing my models with observations, and specifically that I am able using Phantom coupled with MC-FOSS to provide multi-wavelengths synthetic observations that I can compare with the plethora of observations that are now available of many, many sources. And this is fundamental because we can test our models and then predict new observations to try to see directly and indirectly the presence of giant planets in protoplanetary disks. And also I want to underline again that it's very important to work together, theoretical people and observers, because it's fundamental to understand how protoplanetary disks are evolving. And this is relevant because we want also to understand our own solar system, but also all the other exoplanetary systems that we are revealing more and more in those with the new observations. And with this, I thank you for the attention, and I'm happy to take any question.
Thank you, Claudia. Any questions for Claudia? If nobody has one, I have one on your digital work. How many stars did you include? Because
so
we know at least 5 of them.
So this is just A. So digit tau is a quintuplet. So A is a triplet and B is a binary. So this work focuses only on A, but we modeled so digit tau A is a hierarchical tripole, but we consider the secondary as a binary. Sorry, as a single star. So we model a binary.
Okay. Do you expect the little binary to make any difference? Because we see, at least in the sphere image, there's a lot of little streamers that might be caused by the.
So specifically in we did some tests with Simone that is there somewhere. I can't see from the screen. So regarding the cavity size, so the dust ring is not that relevant. Regarding the circumsecondary disk, so the fact that we don't see any dust emission here in the cavity around AB is very relevant because you have a very small tidal radius in between the small secondary. And regarding the streamers, so yes, but I'm not sure that it's so easy to model because you're very, very sensitive to the phase between the secondary and the primary and the disk.
Okay, thank you. Any other questions? Yeah.
Hi, Claudia. Thanks for the talk. I had a question about HT100 546. I'm somewhat familiar with this, but I think I might have missed it. So there's a giant planet at 100 AU, did you say?
So what I modeled is, yes, one giant planet at almost about 100 AU to support the present, so to stop the dust at almost 200 AU. But you can have a multiple system there because the gap is 100 AU, the gap itself.
Okay, yeah, so it's a very big gap. Is that something you could get with direct imaging or say JWST? Is it too far away?
This is a very, so actually there is one candidate. So this is the source that Quants et al. 2013 observed, and they have a source there, but it's closer. It's like 50, 60 AU. They have it with sphere. The problem is how deep is the gas gap, because even if you have a very massive planet, because it's far away, even if it's not a 100 AU, but it's like at 60 or 70 AU, opening a gas gap is very difficult because H over R is large. So can we observe it? Let's see.
Thank you.
Hi, Claudia. I was wondering about the idea of the two giant planets idea. Do you know in the exoplanetary population how common or how frequent that having two giants in resonance is, like out of curiosity?
So I did some short answer, I don't remember, but long answer, I did some tests, and so there are systems in which we have multiple, 2 or up to 3, 4 also planets that are more or less giants. But my question is this, I'm not even sure if this system will be evolved. So even if you have just one giant planet, I'm not sure it's stable enough for surviving at later stage, because this is very far away. It's 100 AU or even 70, you know.
So a sort of subsequent question would be, if you have your two giant planets in resonance during the disk phase, do you expect that to survive over, I mean, once the disk dissipates, or? So
I think, I'm not an expert here, but I think that there are works from the NIS group in which they show the survival rate of tidal locked planets with respect to single planets to this migration phase in class 3. So when you dissipate the gas disk. But I know also that there are a lot of recent literature on free-floating planets of this kind of further away planets, very massive, that when you dissipate the gas becomes unstable and are rejected from the system.
Okay.
So I don't know.
Thank you. We can talk later about that. Thank you.
Later tomorrow.
All right, thank you. Let's thank Claudia again.